Now, why are we interested in natural logarithms at this point in the semester? Because we are going to look at the relationship between the vapor pressure of a liquid, the temperature, and the heat of vaporization, all in the Clausius-Clapeyron equation. Now remember, temperature, anytime we put it in an equation, this will always be Kelvin temperature. Just like with the gas laws, we always had to convert to Kelvin. We convert to Kelvin for this. So this relationship says that the natural log of P, the vapor pressure, is equal to minus the enthalpy of vaporization over the gas constant R times T, the Kelvin temperature, plus some constant C. Now, in the gas chapter, we worked with 0.0821 liter atmosphere per mole Kelvin for the R value, and I also gave you that number in milliliter torr per mole Kelvin. This time, because we're looking at energy and enthalpies of vaporization, our R is a new value. It's 8.314 joules per mole Kelvin. And remember, R is a gas constant, liter atmosphere is work, and so work is energy, so it makes sense we could convert it to joules by putting a different numerical value in there. And when we look at this, this has units of joules per mole Kelvin. When we talk about enthalpies of vaporization, they are usually provided in kilojoules per mole. So you really have to pay attention when you're slapping the numbers in here and make sure that you have the units set so that if your enthalpy of vaporization is in kilojoules and your R value is in joules, you somehow compensate for that and you have to change the units. And I'll show you how I do that. Now we can break this apart to say the natural log of P is equal to minus the enthalpy of vaporization divided by R times 1 over T plus C. So this is now in the slope-intercept form for a straight line, y is equal to mx plus b. So we can plot on the y-axis the natural logarithm of the vapor pressure P, plot that against the reciprocal of the Kelvin temperature, 1 over T, and we will get a line that has a negative slope. And the slope of that line is equal to minus the enthalpy of vaporization over R. So if we multiply the slope times R, we will get negative enthalpy of vaporization, and we can solve for the enthalpy of vaporization from our data that we collect. And this is what we're going to do in lab on Thursday. We're going to measure the vapor pressure of water as we take it to different temperatures and then try and determine the enthalpy of vaporization. So when you think of this, we now have this equation. The natural log of P is equal to minus the enthalpy of vaporization over R times 1 over T plus C. And C is a constant. Remember back in the gas law chapters, we had Boyle's law, Charles' law, the law of Gay-Lussac, and we set them equal to each other in a two-point system. The difference there was Boyle's law was PV is equal to C. Well, here we are setting the PV equal to C, but in this case, with the Clausius-Clapeyron equation, we're adding C. So we can't set this equal to something in a two-point form. So what we have to do is to subtract these. Now, I would be happy to demonstrate to anyone how to subtract simultaneous equations if you like to see that at some later time. But due to the interest of time, I'm going to just show you what the two-point form looks like. If you want to see me do the algebra, I'll be happy to do that for you after class. So we can rearrange this into a two-point form, and it looks like this. The natural log of P1 over P2 is equal to the enthalpy of vaporization over R times 1 over T2 minus 1 over T1. I'll give you just a moment to write that down, and then I want to talk about it. When we looked at the original equation, we had a negative sign in here. You see the negative sign is now gone. If we are subtracting these equations, we would be subtracting T1 minus the T2. And so you'll notice that P1 is on the top, so it's written first here, but T2 is written first here. So by getting rid of this negative sign, I swapped out the positions for T1 and T2. So whatever is on top goes with the first temperature, and whatever's on bottom goes with the second temperature. And it doesn't matter which one is 1 and 2. It doesn't matter what units you use for pressure. The units for temperature must be in Kelvin, as always. So let's look at how this works. When you think about this equation, we have pressure, the enthalpy of vaporization, and the temperature are three different variables. So if we know two of the variables plus the constant R, then we can calculate the missing variable. Here's a typical sort of Clausius-Clapeyron equation 2-point form problem that you might see on the homework or the test. At room temperature, the vapor pressure of hexane is 148 torr. What's the vapor pressure of at 50 degrees C? Well, the first thing we do, like always, is change our temperatures to Kelvin. So this is 298 Kelvin, and this is 323.2 Kelvin. Is it a correct assumption that I don't need to show you how to add to change those at this point? Everybody's good with changing to Kelvin. And the enthalpy of vaporization is 30.1 kilojoules per mole. So now, as I read through here, I always like to identify my variables. P1, T1, P2, and T2. So my original pressure is 148 torr. My original temperature is 298 Kelvin. My new pressure is the unknown. What is the vapor pressure of hexane? And my new temperature, 323.2 Kelvin. So once we've identified our variables, we can go ahead and plug them in. We know the natural log of P1, 148 torr, over P2, our unknown, is equal to the enthalpy of vaporization. Now this was given to me in kilojoules, but I'm going to switch it to joules. 30.1 times 10 to the third joules per mole. All I did was take that and put it in exponential notation. I didn't put it in scientific notation. I just left the 30.1 and slapped on the 10 to the third to switch it, right? Divided by R, 8.314 joules per mole Kelvin. So you can see our joules per mole will cancel, and we have reciprocal Kelvin there, which will become Kelvin, times 1 over T2, 323.2 Kelvin, minus 1 over T1, 298 Kelvin. Now, as we start to work through this mess, again, in terms of sig figs, I do not recommend that you punch this all into your programmable calculator, because you can make big mistakes by not using parentheses properly, and you'll get wrong syntax, which will give you crazy answers. Also, it's much harder to keep track of significant figures when you do that. Now, here at Delta, your math instructors will tell you to separate the logs, to say the natural log of 148 torr minus the natural log of P2. How many of you have been taught that? Okay, and does that work for you? Do you feel real comfortable doing it that way? All right, if you do and you've been taught that and you're comfortable with logs, go ahead and do it that way. For those of you that don't have a lot of experience working with logs, this is the way I do it. I leave this natural log alone until the very end. It's the natural log of what's in parentheses, and that includes my variable, and I'm just going to leave it for now. So the natural log of 148 torr over P2, we leave that alone, is equal to, I can go ahead and start dividing here. So I divide these two numbers and I get 3,620 Kelvin times, now I have 4 sig figs here, so I'm going to have 4 sig figs in my number when I divide this. 0.003094 minus the reciprocal of 298, so I'll have 3 sig figs. Now, when I'm subtracting in those parentheses, I have to preserve place. So here I go out 5 places, and here I go out 6, so I can only go out 5 places. And when I do that, it's only going to leave me 2 significant figures. So the natural log of 148 torr over P2, I'm leaving this alone for now, is equal to 3,620 Kelvin times a negative 0.00027, and that is equal to negative 0.94. So at this point, I have the natural log of what's in these parentheses is equal to negative 0.94. So to get rid of the natural log, I exponentiate, or I take the antilog. So e to the negative 0.94 is equal to what's in my parentheses, 148 torr over P2. So now, grabbing my calculator, e to the negative 0.94 is equal to 0.39. Now I've gotten rid of the natural log, so now I can just rearrange algebraically to find P2. And I find that easier than doing a logarithm and then an antilog. You only have to do one exponential function. So 148 torr divided by 0.39 is equal to P2. So P2 is 380 torr. Now we ask ourselves, does that seem like a reasonable answer? And the answer is, yeah, it does, because this is a bigger number than my original one, and I cranked up the temperature. That's what we'd expect. Okay, I put another one here just like this, but I'm going to not do it now. The answer to this one is 500 torr if you want to try that on your own later. For now, let's go ahead and have you do this in your work groups, in your positions on the board.